So uh, even though in steady state, the entire load is made up by the generator in that area, but under dynamic conditions, all the generators participate. Okay, so this dynamic performance is affected by inertias of various units in this interconnected system. The damping we have, the regulators, the gain of the supplementary control units for ACE and other factors. Okay, so we'll look at that. So let's see that we have just two equivalent generators here. They may represent two areas, for example, and in between we have reactances which can sum up to be, let's say, some value x sub t, and therefore the power flow between these two equivalent generators is given by this equation over here, where delta 1, 2 is nothing more than delta 1 minus delta 2. Okay. So the difference of the phase angle between these two equivalent generators then is responsible for this power flow from 1 to 2 here. So we can linearize this equation around an operating point, initial operating point, and if we do that, we'll find that this increase in power flow that is needed from 1 to 2 is given by this equation. It is again dependent upon the change in this angle, delta 1, 2. So delta 1, 2 is really nothing but change in delta 1 minus change in delta 2, like this here. And it's also dependent upon this so-called coefficient here. So this is equal to this factor times the cosine of this initial angle delta 0, which is the value of delta 1, 2 at initial value here. So this is nothing but this delta 0 here. So you can see that when this coefficient is larger, we have a stiffer system, because this larger coefficient here would mean that for a given required change in power, the change in angle between the two systems would be smaller. Okay, so this will also determine the frequency of oscillations and things like that. Okay, so the best thing to do is to model this, and this is done using Simulink in this example here. So we have two areas connected through a tie line here, and so each one has this area control error, this supplemental control using area control error, ACE1 and ACE2 over here, and then you have the governor and the steam turbine representation over here for each of these units over here, right? And so here we'll see what happens if there is a change in load in area 1. Okay, so only in area 1 there's a change in load, and the change in load in area 2, let's say, is 0. Okay, so depending upon the values of these coefficients here and time constants, let's say that there is a change in area 1 of equal to 1, whatever that is in per unit, or basis, whatever is the basis. That's the change in area is 1. So you can see here that the power coming from the turbine in area 1 eventually settles down to 1 here. So this is 1 here, okay? And so increase in power coming from unit 2 eventually goes to 0. You can see that it's going to 0 here, this value here. And similarly, this tie line power flow between area 1 and 2 oscillates, and eventually this change in that tie line power flow is also going to 0. So that was the objective, that we wanted to keep the frequency to its steady state value, and we wanted to keep the tie line power flow to not change, and therefore the entire load is absorbed by the unit in that area. So the unit 2 in steady state in area 2 is not affected. So now we move on to the next topic, and that is economic dispatch and optimum power flow. So here optimum power flow means the generation for the least overall production cost, and of course this has to be done in regards to not overloading any transmission lines. So they should be within their capacities, and we should always maintain the stability margin, because in case of contingencies, this system should remain stable. So when you look at the cost of generating electricity, there's a component called fixed operating costs, and they depend upon capital investment, etc., and they do not depend upon the power being produced. So power being produced may be zero, but those costs are there anyway. Okay. Then you have variable operating costs, and they certainly include the fuel cost. And so more power you're producing, more is the cost of fuel. And so the operating strategy is that we already have the unit. What are we going to do about it? We already have that fixed cost. So given all that, the operating strategy is to minimize the fuel cost, overall fuel cost, to generate the required amount of power that needs to be produced. Okay, so that's how it is done. And so there is, for each unit, there's something called heat rate. So-called heat rate of the power plant, and it's given in million BTUs per hour per megawatt. Here, million BTUs per hour per megawatt. That's plotted as a function of power here. So you can see that higher the power, the plant becomes a little more efficient, and therefore this heat rate drops as power increases. And so at 40 megawatt of power being produced, this is 10 on the vertical axis. What that means is that at this operating point here, the fuel consumption is 400, 40 times 10, which is 400 million BTUs per hour. Okay, so that's how we need to interpret this heat rate curve. So if you look at the fuel cost curve here, right here, as a function of power, it could be given by, for example, this expression over here. Okay, and so you can see here that it's a function of power here. BI times, so unit I here, so B times the power and C times the power squared. So you can see that this curve would look something like this. So another quantity is defined, and it's called marginal cost. And this marginal cost is really the partial derivative of this fuel cost with respect to power. And for a fuel cost curve defined by this expression, this marginal cost would be this much here. It's a straight line, as you can see, and that's plotted in figure B here. Okay. So the question is that if we have three such units connected, okay, and we will, in this example, assume the losses that we have are constant, which they are not, But so if we assume that these losses are constant, then we can say that for a given amount of losses and the load, the total power production should be equal to the sum of these two here. So the sum of power produced by these three units in this example should be equal, right? So that makes sense. And so, intuitively, we can say that these three units should operate at equal marginal cost. Because if, let's say, one unit is operating at lower marginal cost, then you can argue why not shift more power to that unit, right? So it's somewhat intuitive. But you can also see it by more mathematically by this Lagrange over here, and taking the partial derivative of these things, you can come up that marginal cost for all three units should be equal. And these units have certain limits below which they cannot produce any power, as shown here and shown here, and above which, like P3 over here, they cannot. No, P3 is the whatever. They cannot produce any power beyond that. So, respecting those limits, we can see that they are operating at equal marginal cost here. In addition, we have to worry about spinning reserve and unit commitment. So we have to maintain some spinning reserve, like 15 to 20%, in case the load changes quickly. Okay, so how are we going to supply that increase in load and maintain angle and voltage stability, all kinds of stuff? So that what dictates the spinning reserve. And in addition, we have to think about this unit commitment. If unit spinning reserve is not enough, then we need to add on another unit. Okay, and that is called unit commitment here. So in a nutshell, we have seen the control of interconnected power systems and economic dispatch, and we have seen the control objectives. And one is the voltage control. The other one is automatic generation control to control frequency and tie line flows. And we have also seen glimpses, just a glimpse of economic dispatch, optimum power flow, and unit commitment.